Good morning, students. Myself, Vijay Shankar from Electronics and Communication Engineering Department, Chipro Engineering College. Today we are going to discuss about the Fourier series in the second unit of the Signals and Systems. Fourier series, the second unit of the Signals and Systems. Okay. So first of all, you can see what is a Fourier series and how these Fourier series are used to analyze the periodic signals only. So the Fourier series is a continuous time Fourier series. The Fourier series used to analyze Fourier series are used to analyze periodic signals only. So what is a periodic signals? We already know the basic the classification of the signals, continuous and the discrete time signals. Again, they are classified as a periodic, non-periodic, even and odd signal, deterministic and random signals, and so on. So in that we have the periodic signals. The periodic signal means for continuous time signal, x of t plus capital T is equal to x of t. If this condition is satisfied, then we can say a periodic signal in continuous time. In continuous time, it's a complex function also. See, in the x of n for capital N is equal to x of n. This is for the discrete time signals. Periodic signal condition for the discrete time sequences. See, the Fourier series is used to analyze the periodic signals only. And we have the Fourier transformations. For the Fourier transformation, it's a non-periodic signals also. The harmonic constant of the signals is analyzed with the help of Fourier series. And Fourier series can be developed for continuous time as well as the discrete time signals also. So this is a Fourier series can be developed for the continuous time as well as the discrete time signals. Okay. So mostly you are analyzing for the periodic signals only. Either it is x of t plus capital T is equal to x of t. If both are equal, even if you are adding repeated signals, the t with the period of the t in the continuous with the period of n in the discrete time signals. So what are the different types of the Fourier series? Different types of the Fourier series, trigonometric Fourier series, compact trigonometric Fourier series, also called as polar Fourier series, and the last one is the exponential Fourier series. Trigonometric Fourier series, compact trigonometric Fourier series. The compact trigonometric Fourier series also we can call it as the polar Fourier series. And the last one is the exponential Fourier series. To analyze any signals, we are going for the exponential Fourier series only. Okay, we have the analysis equation, the synthesis equation. We are calling it as analysis equation to analyze the periodic signals by using the Fourier series. Okay, we are using the Fourier series to analyze the periodic signals only. So which satisfies the square of the integral condition. We know here the integral t, the magnitude, squared magnitude of x of t dt is less than infinite. Less than infinite means it definitely is a finite value. Okay, if it is not equal to the infinite, it is less than the infinite, which satisfies this condition, or otherwise we are calling some discrete conditions. Okay, discrete conditions. There is a three discrete conditions are there. One is over any period, x of t must be absolutely integrable. Over any period, x of t is must be absolutely integrable. This is the first condition for the discrete, absolutely integrable. With the integral t, the square magnitude of x of t dt is less than infinite, absolutely integrable. And the second point we can say, if any finite interval of time x of t, if any finite interval of time x of t is of bounded variation, that is, there are no more than a finite number of there are no more than a finite number of maxima and a minimum during any single period of the signal. Okay, and these are the not necessary conditions, are the sufficient conditions. Okay, if any finite interval of the time x of t is a bounded variation, that is, there are no more than a finite number of maxima and a minimum during any single period of the signal. During any single period of the signal. One is the absolute integrable, that condition satisfy the discrete. And the second one is a finite number of maximum and minimum during any single period of the time signal. And the third one, in any finite interval of time, there are only a finite number of discontinuities. In any finite interval of time, there are only a finite number of discontinuities. For this class of signals, we are able to express it is a linear combination of complex exponentials. For this class of signals, we are able to express it is a linear combination of the complex signals. That is x of t is equal to sum of k equal to minus infinite to infinite. A suffix k, we can write it as a of k also. A suffix k e power j k naught or k omega naught t. The value is a suffix k, or you can write it as a of k also, e power j k omega naught t. And this one is with the period of 2 pi by omega naught. With the period of 2 pi by omega naught. The t is equal to the interval of t is equal to 2 pi by omega naught. Or omega naught is nothing but 2 pi f naught. So 2 pi get cancelled. It is inversely proportional to the frequency, the time only. There is a three conditions, discrete conditions. One is absolutely integrable, and another one is a finite number of maxima and minima during any single period of the signal. And the third one is in any finite interval of time, there are only a finite number of discontinuities. Using this here, x of t is equal to the sum of k equal to minus infinite to infinite, a of k e power j k omega naught t. Omega is the period of 2 pi by omega naught, or nothing but is a full cycle. See, Here omega naught is the fundamental frequency. Omega naught is equal to 2 pi by t, or t is equal to 2 pi by omega naught. And the coefficients A of k known as a Fourier series coefficients. The coefficients A of k are known as a Fourier series coefficients. Okay, my dear students. Now, the continuous time Fourier series coefficient formula, the x of t, from that it is x of t is equal to the sum of k equal to minus infinite to infinite A of k e power jk omega naught t, e power jk omega naught t. In this the Fourier series coefficient, whatever we are saying here, the coefficient A of k is known as a Fourier series coefficient, and that A of k is given as 1 by t, the integral t. That will get the x of t here, the x of t into e power minus jk omega naught t dt. A of k is equal to 1 by t, the integral t, x of t into e power minus jk omega naught t dt. The coefficient, the Fourier series coefficient. The Fourier series is x of t is equal to sum of k equal to minus infinite to infinite A of k e power jk omega naught. And you can derive this equation. Okay, how we got this equation A of k in the literature. Okay, the Fourier series representation. We are saying that the Fourier series is used to analyze the periodic signals. What is the periodic signal condition here? X of t plus t, capital T, is equal to x of t. In general, not every signal can be decomposed as a linear combination of complex exponentials. However, such decomposition is still possible for an extremely large class of signals. We want to study one class of signals that allows the decomposition. They are periodic signals. That periodic signal satisfies the condition of x of t plus capital T is equal to x of t. Okay, for the continuous time signal. So what is a trigonometric Fourier series? What is the first Fourier series is a trigonometric, and second one is a compact trigonometric Fourier series or polar Fourier series, and the third one is a exponential Fourier series. We are discussing about for the continuous time signals, my dear students. So x of t is equal to, is a combination of A of k, B of k, and the A of 0 with cosine and the sine functions. The x of t is equal to A of 0 plus sum of k is equal to 0, 1 to infinite A of k cos k omega naught t, and sum of k is equal to 1 to infinite B of k sine k omega naught t. See why you got this A of 0 means we can start it as a k is equal to 0. When k is equal to 0. In this function, there is a cos is there, cos of cos k is equal to 0, omega naught t. You can start that k is equal to 0 to infinite. When the k is equal to 0, we can substitute a cos 0. What is a cos 0? Cos 0 is equal to 1. Cos 0 is equal to 1. So this function is a 1, A of 0. In this, the coefficient is a of 0. So A of 0 into cos 0, that is a 1. And that is a value, the cos of 0 is a 1, and it is a of 0. Following my dear students. So when k is equal to 0, we'll get the A of 0 plus, and it starts from the k is equal to 1 to infinite A of k cos k omega naught t, and k is depends upon these values 1 to infinite. And in the third term, we have sum of k is equal to 1 to infinite, and here also the k is equal to, it start from the k is equal to 0 only. In this k is equal to 0, it becomes of b of 0 and sine 0 into omega naught t, k value is 0 here. What is the sine 0 is 0 and b of 0 into 0. Total becomes of the 0 value. So plus 0 we have, actually there is no any value for adding of the 0 value. So x of t is equal to 3 terms. So we have a of 0 plus sum of k is equal to 1 to infinite a of k cos k omega naught t plus sum of k is equal to 1 to infinite b of k sin k omega naught t. For cosine functions, the coefficient is a of k. For sine function, the coefficient is a b of k. Where in the trigonometric Fourier series, where in this a of 0 is a 1 by t, the integral t x of t dt, and a of k is equal to 2 by t, the integral t x of t dt. 2 by t, the integral t x of t cos k omega naught t dt. And b of k is equal to 2 by t, the integral t x of t sin k omega naught t dt. So how we got these equations? Let us derive that equations. So the first one is a trigonometric Fourier series, that is derivation part. So in the orthogonality function, we've seen that there is an approximation signal. Approximation signal f of t is equal to, actually there is a right angle triangle, we have a right angle triangle here. When it is a right angle triangle, these are not the right angle triangle actually. Having the right angle triangle like this, the orthogonality function, and this is a theta we have, and this signal is f of t signal, and the error signal e of t, and here this point you can assume that as a c. In approximation signal, the cn and the xn of t, cn xn of t. Okay, my dear students, is the origin. When f of t and this x of t signals both are orthogonal, when the theta is equal to 90 degrees. If theta is not the 90 degrees, there is an error signal we have, error component in the f of t. If there is no any error component with the f of t and x of t is both are mutually perpendicular to each other, and also call it as a orthogonal function. Okay. Now, according to our right angle triangle, in the right angle triangle, f of t is equal to the side plus side. What is the side here? E of t plus cn x1 of t, but the c1, x1, c2, x2 and so on. So that I am representing as x of sum of n is equal to 1 to infinite, or it is a n cn xn of t. Cn xn of t. Okay, my dear students. So this error signal is approximation signal. Okay, approximately, if these two are equal, not that these two are equal, approximately f of t is equal to, the error is a 0. Consider it as error is a 0 here, plus the sum of n is equal to 1 to infinite cn xn of t only. We already derived this equation in the orthogonality. orthogonality of orthogonality concept on the approximation signal. Okay. F of t is equal to, or approximately equal to, sum of n is equal to 1 to infinite Cn xn of t. Okay. Here xn of t represents orthogonal set. This equation is called generalized Fourier series. When we are discussing about the orthogonality also, I told that remember this equation is used for in the Fourier series, the generalized Fourier series. Okay. And we derive some complete set of orthogonality for a given set of cosine functions and the sine functions. See, having one set with cosine functions and the sine functions is orthogonal over a power of t naught. Here omega naught is called fundamental frequency and pi omega naught is called nth harmonic. There is a DC component of cos n omega naught t at n is equal to 0. Cos 0 omega naught is equal to 1. This signal is set. The signal set consists of sine, cosine terms, hence it is called trigonometric set. Hence it is called as a trigonometric set. See here, this is the equation, the same equation, whatever I wrote here. The f of t is equal to sum of n is equal to 1 to n Cn xn of t. And that Cn, I take it as a naught, a1, a2, and so on for the xn of t assuming of cosine function. The xn of t is a signal is a sine functions, not the sine, sorry, cos functions. And b naught is also we have that b naught is into 0. Here actually it is a b suffix 0 into 0 because sine 0 is a 0 here. So we are not taking this b naught into the 0. b1 sine omega naught t plus b2 sine 2 omega naught t and so on. How we got this cosine function and this cos function means the one signal, whatever the signal we are taking here, the xn of t, we take it as one time as cos n omega naught t with the coefficients of a of k. And nothing but is a suffix cn is a not the a of k. Little bit will get the confusion. Cn, nothing but it is a an. I'm taking it as a cn whatever here, but cn is a an. And another time with having sine functions, xn of t, assuming it as bn sine n omega naught t. Bn sine n omega naught t. After expanding this from n is equal to 1 to infinite, that f of t is equal to a naught a1 cos n omega naught t and so on. And you can write it as a naught plus sum of n is equal to 1 to infinite an cos n omega naught t plus sum of n is equal to 1 to infinite bn sine n omega naught t. And this is a bn for the sine coefficient and an for the cosine coefficient. The values of an and the bn can be obtained here. An is equal to an. What is the an? We already know the signal here, approximation signal, orthogonality function. Cn is equal to, we already derived that is a t1 to t2, t to t plus t naught, or t1 to t2, whatever it is. So t to t plus t naught, f of t, xn of t, dt. If the numerator is a 0, then Cn is equal to 0. It is not at all equal to the below function because it is energy signal. T to t plus t naught x n square of t. We all learn, is a Cn is equal to an orthogonality function the n of t is a sine function and the Cn is becomes of the Bn. Okay, in that An as equating the same function what we already learned, Cn is equal to integral t to t plus t naught f of t x n of t dt by integral t to t plus t naught xn square of t dt. That by the integral t to t plus t naught xn square of t dt only. Since it is a Bn here, what is the xn of t is sine n omega naught t. Sine n omega naught t. Let us see here. Bn is equal to, now see the Bn is equal to integral t to t plus t naught f of t sine n omega naught t dt and whole divided by integral t to t plus t naught sine square n omega naught t. This is a Bn value, my dear students. Okay. Okay. Expand the denominator here. We know the denominator is a cos square t. Let it be the cos square dt. So directly there is no any integral of the cos square. So convert the cos square as a trigonometric function 1 plus cos 2t. 1 plus cos 2t. See here, there the cos square theta is equal to 1 by 2. 1 plus cos 2 theta by 2. 2 theta by 2, my dear students. So I am taking this a 1 by 2 here. The integral t to t plus t naught 1 plus cos 2. What is the theta instead of theta here? N sine, not the n sine, n omega naught t. N omega naught t. Cos 2 n omega naught t dt. So separate these two integrals 1 by 2 into integral t to t plus t naught dt plus 1 by 2 integral t to t plus t naught cos n omega naught t. See, in a full cycle, I already said that in the complete set of orthogonality example, cosine functions, sine functions, and sine and cosine functions, 3 cases we taken. And the first one, cosine function, in a full cycle, the integral of cos is 0. And the second case, we take sine functions. In that also, the full cycle, the sine function is a 0. And in the third case, we took sine and cosine functions, and the sine and cosine functions in the integral of 0 to 2 pi, or the t to t plus t naught, it is also the 0. Okay. So the second term what we have here, 1 by 2 the integral t to t plus t naught is a cos 2n omega naught t, integral of cos integral of cos with this a full cycle, definitely that is a 0. Here note that the second term is integration of full cycles of cosine wave over one period. It is a 0. Always a 0. Following my dear students, always a 0. And the first term we can see here, the 1 by 2, the integral t plus t naught 1 into dt. So constant means a t, lower limit is a t, upper limit is a t plus t naught. So you can substitute the t plus t naught minus t get cancelled, and we have only the t naught by 2 for the denominator. What we have, the integral t to t plus t naught cos square n omega naught t dt is a t naught by 2. So an is equal to, see in the previous slide, the an is equal to, the numerator we have integral t to t plus t naught f of t cos n omega naught t dt, and this denominator we simplified now. Integral t to t plus t naught cos square n omega naught t dt. Substitute that integral cos square n omega naught dt with limits of t to t plus t naught as of t naught by 2 as a denominator, and bring that it is a numerator 2 by t naught integral t to t plus t naught f of t cos n omega naught t as of an value. And similarly, the bn is also calculated as the bn is equal to integral t to t plus t naught f of t sin n omega naught t. In this case, and this xn of t as taking as a sine functions, sine square n omega naught t, and this sine square n omega naught t is also directly we are not applying by using the trigonometric function. Simplify that one, and that also will get as integral sine or the cosine functions. Always we can say the period of t to t plus t naught is always a 0. So here also you'll get the 2 by t naught, bn is equal to 2 by t naught integral t to t plus t naught x of t sin n omega naught t dt. Sin n omega naught t dt. So an and the bn will get both the equations. So what is the a of a0? A0 means simply substitute n is equal to 0 in this equation only. When n is equal to 0 here, it becomes of a0 2 by t naught integral t to t plus t naught x of t cos n omega naught t. Cos n omega naught t. And in this cos n omega naught t, cos n is a 0, and this becomes of cos 0 is equal to 1, and the integral t to t plus t naught into dt, it becomes of 2 by t naught. Okay, the 2 by the t naught function. But here we are not taking that as a 2. Why it is, I will explain that later. The a naught is equal to, we can take it as a 1 by t naught integral t to t plus t naught x of t dt. This depends upon here the limitations. Here the limitations, there is a changes occurs in the multiplication factor of 1 by t naught and the 2 by t naught values. Okay, when n is equal to 0 in this equation only, we get a of 0. Okay, my dear students. See, whatever we discussed in the previously, these values here, the trigonometric Fourier series, x of t is equal to a of 0 for k is plus sum of k is equal to 1 to infinite, a of k cos k omega naught t plus sum of k is equal to infinite, b of k sin k omega naught t sin k omega naught t. In this, a of 0 is 1 by t, the integral t x of t dt, and a of k is equal to 2 by t, the integral t x of t cos k omega naught t dt, and b of k is equal to 2 by t, the integral t x of t sine k omega naught t. These are all combining, we can call it as a trigonometric Fourier series. We derive these equations from the generalized Fourier series, what we already discussed in the orthogonality function approximation signals concept. F of t is equal to sum of n is equal to 1 to infinite Cn xn of t. Cn xn of t. Okay, that Cn is a coefficient of the signal what we are assuming. If it is a cosine function, the Cn becomes of an, and we can assume the xn of t is a sine function, the coefficient it becomes of the bn values. Okay, my dear students. Then compact trigonometric Fourier series. So the second type of the Fourier series is a compact trigonometric Fourier series. So no need of the derivation part of the compact trigonometric Fourier series. So we are using this in any analysis by using the Fourier series for the periodic signals. The trigonometric Fourier series can be represented in the compact form. It is also called as a compact or polar form. Polar means we'll get magnitude and the phase. What is the magnitude here? That magnitude is a d of k. Polar is nothing but converting of rectangle to polar. The rectangular function, the trigonometric Fourier series, we can consider it as in that the d of 0 and the d of k. The d of k is under root of a of k square plus b of k square. Already in the equation, we have a naught, an and the bn. Consider it as a k values. K means a suffix k. It changes as cos. Instead of n, we write it as a n k values. Okay. And pi of k is a phase angle minus tan inverse imaginary coefficient b of k by the a of k. Okay. And the x of t. The x of t signal becomes of d of 0 as of a of 0 is similar to that of in the polar form also, plus sum of k is equal to 1 to infinite d of k as magnitude cos k omega naught t plus as a phase angle the phi of k. This is the equation for the complex, not the complex, compact trigonometric Fourier series or the polar Fourier series. And coming to the last one, the exponential Fourier series, to analyze Fourier series is used to analyze the periodic signal with this exponential Fourier series only. This we have, I already said that it is having the synthesis equation and the analysis equation. Mostly we are using for the analysis equation only. Analysis equation. The inverse, it is a Fourier series inverse. Synthesis equation we are using. What? Let us see. X of t, the Fourier series we can apply. Fourier series, it becomes of x of k. And x of k is Fourier series, you can inverse Fourier series also, you can get it as a x of t. X of t and here the x of k. X of k and here x of t internally. The x of t into e power minus j k omega naught t. X of t into e power minus j k omega naught t dt. So x of t is equal to sum of k is equal to minus infinite to infinite x of k into e power j k omega naught t. What is that e power j k omega naught t? E power jx. What is the e power jx is nothing but a cosine and the sine functions. Cos x plus j sine x. Cos x plus j sine x. X of k into cos x plus j into x of k sine x. So very important, the synthesis equation x of t is equal to sum of k equal to minus infinite to infinite x of k e power jk omega naught t. Here it is a positive exponential in the synthesis equation. Coming to the analysis equation, in that only the x of k is equal to 1 by t, the integral t, the x of t into, actually here there is x of t is also there, x of t into e power minus, there is a minus negative exponential in the analysis equation, e power minus jk omega naught t dt. Okay, it is a Fourier series. For the given signal, to find out the Fourier series as x of k, the Fourier series coefficient x of k is equal to 1 by t, the integral t x of t e power minus jk omega naught t dt. Okay, we already discussed about the discrete conditions. There is a single valued property with a x of t must have only one value at any time instant within the time interval t naught, and finite discontinuities, finite peak for maxima and minima in the interval t naught, and absolutely integrable. We already discussed about this. The convergence of a Fourier series, or is also called as a discrete conditions, single valued property, finite discontinuities, and finite peaks, and absolutely integrable. The single valued property, the x of t must have only one value at any time instant within the time interval t naught. That is nothing but the single valued property. X of t must have only one value at any time instant. At any time instant, there is an x of t having only the one value. It is a single valued property within the interval of the t naught. And second one is a finite discontinuities. X of t should have at a most finite number of discontinuities in the interval of t naught. Because of this, the signal can be represented mathematically here. You already learned that it is a finite discontinuities. And then coming to the finite peaks, the signal x of t should have only the finite number of maxima and the minimum peaks, nothing but within the interval of the t naught. And the absolute integrability, the signal x of t should be absolutely integrable. That is, the integral to t naught, magnitude of x of t is less than the infinite, and nothing but is a finite value. This is because of the analysis of equations integrates x of t. Okay, my dear students, these are very, very important. Simply you can write as, if they ask what is are the discrete conditions, single valid property, finite discontinuities, finite peaks, and absolute integrable. Simple. Now the properties of the Fourier series. Properties of Fourier series. Before the properties of the Fourier series, some explanation part is given for here. We are saying the single valid property and finite discontinuities, finite peaks, and absolute integrable. The function x of t is a single valued function, that is, the function x of t must have a single value at any instant of time. For example, you see here, for example, consider and this characteristics, which is not a single valued because it having the two values at the time t naught. See here the one value and here the one value is there. The two values, double valued. Following my dear students, for these characteristics at the interval of the t naught, there is a two valued functions. Two valued, and it's a positive there and the negative value also. And the figure B represents a single valued function as it has only one value at a time t naught. See the 0 to t naught, at the interval of t naught, it having only the one value. Nothing but the single valued property. the x of t having only the single value with an interval of t naught. This is an example of the first condition for the Discrete condition when we consider this as a two valued. So in the signum function, see, I already explained that is a signum function. It shows at the 0, there is a +1 and the -1 also. +1 and the -1. So actually it is not the plus, it's greater than the 0 and the less than the 0. Okay, at a time it is a t naught, it having shows there is a two value, double valued, single valued is like this. With the interval, it having only the single valued. Following my student. And second one, a finite discontinuities. The single valued property. X of t must have only one value at any time instant. At any time instant, it is the t naught and the next 2t naught and 3t naught and so on values. It have only one value only. And the finite discontinuities, x of t must have at the most finite number of discontinuities in the interval t naught. Because of this, the signal can be represented mathematically. You see, consider the figure here below. This is a figure 4.2. The function has no finite number of discontinuities. No finite number of discontinuities. But in the figure B, you can see here finite number of discontinuities. So consider the 4.8 has no finite number of discontinuities, and it is not possible to find the value of a function x of t at such a number of discontinuities. It is not possible to find the value of function x of t at such a number of discontinuities. Hence, it cannot be represented by a Fourier series. Hence, it cannot be represented by a Fourier series in this function. But here, for the x of t, the function shown in the second, the figure 4.b, has a finite number of discontinuities. But here there is no finite number of discontinuities. Due to this, it is not possible to find out the function of x of t. And here the finite number of discontinuities and the value of x of t at the discontinuity can be calculated by using the formula here. The x of t is equal to t, x of t minus plus x of t plus by 2. Taking off the average of the two functions, minus and the plus, then we can consider it as the maximum value, and here it is a minimum. And there is a discontinuity here, and we can take this as x of t. And from here it is a finite, and there is a, you can find out the x of t values. Understood, my students? And similarly, the function x of t has a finite number of minima and the maxima. A finite number of minima and the maxima. That is a third condition. The function shown in the 4.3a, the first one, has no fixed number of maximum and the minimum. There is no any fixed number of maximum and minimum in these two characteristics, as of the function having no fixed number of minimum and the maximum. So the function shown, so it cannot be represented by the Fourier series. And having only the fixed number of maximum and minimum, then it satisfies that condition, Discrete conditions. Whereas in this figure, you can see there is a maximum and here it is a minimum. Whereas the function shows in the 4.38 has one minimum and one maximum and the finite number of maxima and minima. I'm saying it is within the interval of 10. Okay. So it is represented by a Fourier series. It is represented by a Fourier series. But in this condition, we can't say there is no any fixed number of maximum and the minimum, But in this, there is a fixed number of maxima and minima. There is a one minimum and one maximum. Okay, that is the second one. Not the second, the third one, my dear students. Sorry, third condition. Single valued property, finite discontinuities, and finite peaks, nothing but maximum and the minimum. The last one we have absolute integrable. The function x of t is absolute integrable in the interval of t1 and the t2. The function shown in the figures, it is not absolutely integrable within the interval t1 to t2. Consider the first one here. Hence, it cannot be represented by a Fourier series. But the function shown in this the second characteristics is absolutely integrable within the interval of 0 to t, a sine function. Okay, so integral 0 to t x of t dt is less than infinite and hence can be represented as a Fourier series. Absolutely not integrable and this function whatever shown in this in the figure B is absolutely integrable. Okay, these are the four discrete conditions: single valued property, finite discontinuities, and finite peaks, maxima and minima, and the last one is absolutely integrable, nothing but the integral 0 to t, the x of t, the magnitude of x of t is finite value or it is a less than the infinite. Coming to the very important topic, is a very important topic in the Fourier series, in the second unit Fourier series, the properties, the x of t, the Fourier series x of k, the first property, linearity property, my dear students, linearity property. If x of t, take the Fourier series x of k and the y of t as a time signal, the y of t, apply the Fourier series, we'll get the y of k. Then we can prove that z of t, you can take it as a combination of the x of t and y of t with the coefficients of a and b. Apply the Fourier series to get z of k is equal to a into x of k plus b into y of k. You have to show that z of k is equal to a into x of k plus b into y of k. Now, according to the analysis equation, I already told analysis equations, my dear students. So mostly we are using this equation only in the Fourier series. Analysis equation, see here. X of k is equal to 1 by t, the integral t, e power minus j k omega naught t dt. Okay. In some cases, we are using the synthesis equation. So the z of k is equal to, instead of x of k, I am taking here the z of k, 1 by t, the integral t, z of t e power minus j k omega naught t dt. Fine. So I will show it in the whiteboard. The first property is saying the linearity property. So linearity property. So very, very important, my dear students. Linearity property. What they are giving the statement x of t. Apply the Fourier series x of k and the y of t. Apply the Fourier series, it is y of k. Then prove that Z of t is equal to taking off a into x of t plus b into y of t. Apply the Fourier series for z of t to get the z of s is equal to a into x of, not the s, sorry, z of k is equal to a into x of k plus b into y of k. B into y of k. Okay, my dear students. Take the proof. According to the synthesis and the analysis equation, we are going for the analysis equation only. But analysis equation is x of k is equal to, actually, x of k is equal to 1 by t, the integral t, x of t, e power minus jk omega naught t dt. This is the equation for the Fourier series coefficient. X of k is equal to, x of k is a Fourier series coefficient. So instead of x of k, I am taking the z of k is equal to integral 1 by t, the integral t. So it is x of k, internally we have the x of t. So z of k means z of t is a signal, e power minus jk omega naught t dt. Understood, my students? Is equal to 1 by t integral t. What is the z of t is given? A into x of t plus b into y of t. So substitute here a into x of t, not the capital letter. Here you can use only the small letters only, my students. Signal means small letter, coefficient means capital letter. A into x of t plus b into y of t whole multiplied with e power minus jk omega naught t dt. Okay, and expand this, and 1 by t integral t. First I am writing the a into x of t e power minus jk omega naught t. A into x of t e power minus jk omega naught t dt plus, I am multiplying this b of y of t into this one. So again the 1 by t is also will get for the second term also. 1 by t, the integral t, b into y of t e power minus jk omega naught t dt. Okay, my dear students. So see, and this is equation the similar to that of x of k, 1 by t, the integral t x of t e power minus jk omega naught t dt only. So a is only the multiplication factor, implies or is equal to a into, and this total equation becomes of x of k, a into x of k plus, and here also you can see in this equation is x of k, here x of t. So suppose instead of x of t, the y of t is there, means this is equivalent to that of y of k with the multiplication of b into y of k only. Okay, is the final, you can prove that is a into x of k plus b into y of k. It is a very important and easy also how we can prove this, the linearity property in the Fourier series. Understood, my dear students? See, the same thing here also, 1 by t, the integral t, z of t can substitute a into x of t plus a into x of t plus b into y of t e power minus jk omega naught t dt. Expand this with a as the multiplication factor, 1 by t, the integral t x of t power minus jk omega naught dt plus b into 1 by t the integral ty of t power minus jk omega naught t dt. Right, this function 1 by t the integral t x of t power minus jk omega naught t as x of k, and this function 1 by t the integral t y of t power minus jk omega naught t dt as y of k. This property is used to analyze the signals which are represented as a linear combination of other signals. There is a significance for the linearity property. This property is used to analyze the signals which are represented as a linear combination of the other signals. Linear combination of the other signals is the significance of linearity property. Understood, my dear students? And coming to the shifting property, we already know time shift means linearly you can shift right and shift left. Shifting the signals towards the right side means we can call it as a delay signal. Shifting the signal towards the left side means we can call it as a advanced signal. Otherwise, it is a linearly you can move the signal towards right and towards the left. Is also called as a translation. Here, the time shift property. How many samples you can shift the mathematically in the mathematical expressions? If x of t if x of t is a Fourier series of x of k, then z of t is equal to x of t minus t naught. How many samples it is shifted towards the right side? Why I'm saying it is the right side? It is x of t minus t naught. Minus is there. That is shown. And minus is not there. The minus and the a value or the k value. A as taken with the continuous time signal, and k value is taken as for the discrete time signals. X of t minus a and x of n minus k. And this a value is a positive, it becomes of t minus c. And a value is a negative, it becomes of t plus. A value is a positive means it is right side shifted. Right side shifted. A is positive. And if A is negative, it shifted towards the left side. A is negative. Similar here also. If K is positive, shifted towards right side. If K is negative, shifted towards left side. It depends upon the A value. I'm not saying it's here the minus. The A is positive and the A is negative, then it shows that it is a minus or the plus. Whenever it is A is positive, there is a T minus we will get. So here also x of T minus T naught. Means T naught samples is shifted towards the right side. What happens when this signal is applied, the Fourier series z of k is equal to e power minus jk omega naught T naught into x of k. This factor is multiplied for the x of k signal. E power minus jk omega naught T naught is multiplied to the x of k. Following, my dear students. How it is, let us see. In the whiteboard, I will explain it. Time shift property. Time shift. X of t minus t naught the Fourier series, so you can apply. It is e power minus jk omega naught t naught into x of k. They are saying you have to prove this. So what is the analysis equation? The proof analysis equation, x of k is equal to 1 by t, the integral t, x of t, you can take it as x of t minus t naught into e power minus jk omega naught t dt. Assume that let m is equal to t minus t naught. T naught is a constant, my dear students. So dm is equal to dt. I'm applying the derivative of m dt. The t naught is a constant, is a 0. So is equal to 1 by t, the integral t, and x of t minus t naught means m e power minus jk omega naught. What is a t? T is equal to m plus t naught. From this equation, m plus t naught dt, now it is changes as a dm, is equal to 1 by t, the integral t, x of m e power minus jk omega naught. I'm writing as a m here one time, m into dm also. And another, you can split it these two parts as e power minus jk omega naught t naught. Okay, this is a multiplication factor you get. See, observe here the 1 by t, the integral t x of m e power minus jk omega naught m dm. Instead of t, here the m is there. It is also the equation of x of k is equal to x of k into e power minus jk omega naught t naught only. This is the equation we have. It's the same thing. Understood, my dear students? It is also very important. Time shift or translation is here. If they are taking the z of k is equal to 1 by t, the integral t x of t minus t naught e power minus jk omega naught t dt. T minus t naught is equal to m. Limits integrates with shift by t naught, but again the integration is over the period, hence the limits can be kept as the same. Okay, why I'm taking the same limitations even if you're changing the m also? For m or the t, both it having the limitations is the same. So 1 by t, the integral t x of m e power minus jk omega naught m, and another e power minus jk omega naught t naught. The two parts will get. The quantity inside the squaring brackets is called the x of k. Hence, z of k is equal to x of k into e power minus jk omega naught t. Following, my dear students. So today we learn about so what is a Fourier series introduction, and what are the conditions, the Discrete conditions, and what are the different types of the Fourier series, trigonometric Fourier series, and compact trigonometric Fourier series, and the exponential Fourier series, and what are the different Discrete conditions, nothing but the convergence of the Fourier series, a single valued property, finite discontinuities and finite peaks, and the last one is absolutely integrable. And also we discuss about the properties of the Fourier series as two properties. One is a linearity property and another one is a time shift property. Okay, so any doubts, please raise, my dear students. Okay, we'll continue tomorrow. Thank you one and all.